multi-step reactions involving alkynes. This is page 113 and 114. Starting on page 113, we have 2-butane being converted to 2 moles of acetic acid. We immediately notice that a 4-carbon alkyne is converted to 2 carbon products. So this would be a cleavage reaction, split equally. Sigma and pi bonds must be cleaved. We want to do that with a strong oxidant. Recall that hot permanganate. So hot KMnO4 will do that. If we use acidic solution, the products will in fact be acids, as we have here. Had we used basic solution, the acid would be deprotonated to carboxylates, and in this case acetate. So this clearly is a case where it's acidic. Well, that was a single step reaction. Let's try the next one. Again, we start with 2-butane, and we're forming in this case cis-2-butene. So this is a partial reduction. If we use hydrogen on Lindlar catalyst, which is a deactivated form of palladium, it does indeed produce the cis-alkene. Had we used instead sodium on liquid ammonia, that would give us the trans-alkene. So those are the 2 options for partial reduction of an alkyne to an alkene. Again, a single step reaction. Take a look at number C. We're going from 2-butane to 2-bromobutane, or sec-butyl bromide. So you might at first glance think, well, I just add HBr, but that won't really work, will it? Because adding HBr will add 1 bromine, but you'll have to add HBr twice, in which case you have 2 bromines. Nor can you directly add bromine, because then you'd have 4 bromines added. So what's the key to this? Well, how about if we took the product from the previous reaction, the alkene, and then added HBr? That would do it. Alternately, you could first add 1 equivalent of HBr, because the reaction does stop after 1 equivalent. And then hydrogenate. Hydrogen on any of the standard catalysts. In the next example, we are converting 2-butane into 2-butanol, or sec-butyl alcohol. So it is a hydration, but we certainly can't do that in a single step, can we? Hydration of an alkyne produces an enol. We don't have an enol. The enol rearranges to a ketone. That's not going to work. What if we first reduced our alkyne to the alkene using hydrogen on Lindlar, or you could use sodium in liquid ammonia, forming 2-butene, a partial reduction, and then the alkene can be hydrated to the alcohol using any of our standard methods. Dilute aqueous acid, dilute aqueous sulfuric acid. Let's try E. Here we're taking 2 butane and we're going to form 2, 3 dichlorobutane. Notice we can't just add chlorine directly, because if we do, there's no way of stopping after one addition. You'll wind up adding 4 chlorines instead of 2. Nor can we just add HCl. Let's see. That won't give us the right product, will it? If you add just HCl, the hydrogen will add to one of the carbons. Let's say hydrogen adds here and chlorine to the opposite carbon. That would give us an intermediate alkene. Okay, that looks good, but then when you add the next molecule of HCl, the hydrogen will add here to the less substituted carbon. And then the chlorine will add here. So we'll in fact get the gem dihalide instead of the Vic dihalide. So that's not going to work. How are we going to do this? Why don't we first do a partial reduction to the alkene, again using hydrogen on Lindlar catalyst or sodium in liquid ammonia. Now we can chlorinate, and that'll be the anti-addition product. Page 114, first question, we want to convert this 2-carbon alkyne, acetylene, into an alkene with more carbons. So 2 things are needed here. We need to partially reduce, we need to partially hydrogenate the alkyne to the alkene, and then we'll need to add more carbons. The only way we've learned to add carbon so far is by alkylation of an alkyne. And this is a terminal alkyne, so that can be done. If we add very strong base, sodium amide, its pKb is -21. That's strong enough to deprotonate this very weak terminal hydrogen, which is weakly acidic. 25 is a pKa. Here's the acid-base mechanism. The base removes the hydrogen ion. A pair of electrons stay behind. Will form sodium acetylide. And ammonia, but we're not worried about the ammonia. Now, the alkynide itself is still a strong base, not as strong as the amide, but still significantly strong. Its pKb is -11, and all strong bases are good nucleophiles. So our next step then would be to combine this with a primary alkyl halide. It'll undergo a substitution reaction. We need to add this carbon group to our alkynide. So we'll do that as a halide. That's a primary alkyl halide. As a point of interest, how would we name that? This could be bromomethyl complex substituent cyclopentane. Likely that is the correct name, but I suspect one could get away with calling this bromo cyclopentyl methane. Yeah, it seems a bit dodgy, but probably okay. In any case, our good nucleophile will undergo a substitution reaction with the primary alkyl halide, displacing the bromide, and we'll have our carbon group that we need. Okay, and then it's simply a matter of partial reduction of the alkyne to the alkene, and again, either hydrogen on Lindlar or sodium in liquid ammonia. Since the stereochemistry of the product is not specified, it doesn't matter which one we use in this case. Let's try B. Here we have 2-bromobutane going to, this is 2,2-diiodobutane. This is not chlorine, this is carbon followed by 2 iodides. So we have here a gem dihalide. And do you recall that a gem dihalide was formed from an alkyne? That would be the immediate precursor if we added 2 equivalents of the hydrogen halide, hydrogen iodide in this case. So then it's simply a matter of converting the alkyl halide, 2-bromobutane, into 2-butyne. Well, we can carry out dehydrohalogenation, KOH, in ethanol to form the alkene, how do we go from the alkene to the alkyne? We would carry out a halogenation. This time I'll just say chlorine for something different. Chlorine or bromine. And then we carry out a double dehydrohalogenation using 2 moles of KOH at a high temperature, 200 degrees Celsius. So there it is. In question C, we are going to convert trans stilbene, that's trans 1,2-diphenylethene, into cis 1,2-diphenylethene. How are we going to do that? It'll help us if we remember that to form the cis alkene, we can do it from the alkyne. And how do we do that? Hydrogen on Lindlar catalyst partially reduces the alkyne to the cis alkene. So now it's simply a matter of converting the alkene to the alkyne, and we've looked at that several times. We can halogenate this, bromine or chlorine. And then a double dehydrohalogenation. 2 KOH, 200 degrees Celsius, minus 2 HBr gives us the alkyne. So this should be D, the last one on page 114. How do we convert 2-bromobutane to this ketone? And by the way, the name of this would be 2-butanone. Again, you're not responsible for nomenclature of ketones in this course. In any case, how do we form 2-butanone? Do you recall that ketones were formed after the hydration of an alkyne to an enol, and the enol spontaneously rearranged to the ketone. So if we had here an alkyne and we hydrated it, let me show the intermediate here. We hydrate it with water, dilute aqueous acid, and mercury 2-sulfate catalyst. It actually gives the enol and that rearranges spontaneously to the ketone. Something like this. Yeah. So if we had an alkyne, we could hydrate it to the enol, which rearranges to the ketone. So now it's simply a matter of how do we convert the alkyl halide to the alkyne. Well, we've done this a few times now. KOH in ethanol, dehydrohalogenation loses HBr. It gives us the alkene. That would be 2-butene. To convert the alkene to the alkyne, that requires 2 steps. Halogenation, for example, bromine in dichloromethane, as we did in class. And then finally, double dehydrohalogenation, 2-KOH, at a high temperature, 200 degrees C, minus 2 HBr to the alkyne. And that's it for the multi-step reactions of alkynes.